Hi everybody, welcome back to Chem 161. It is week 8, and that means that we're almost done. Like, holy crap. Just a second. Sorry, I had to sneeze there. What are we doing tonight? We are doing lab worksheet number 4, and also Q&A. I forgot to write it up there. I accidentally moved part of my stream layout because I didn't have it locked down. And that ruins everything, it turns out. So I had to fix that, and that took like 5 minutes. And I can't undo for some reason. So I apologize for the late start. We're going to begin by talking about lab number 4. So lab number 4 is an entirely Excel exercise. So everything that you do is going to be just Excel commands. And whenever I say Excel, what I really mean is Google Sheets. Please use Google Sheets to do this. Don't use your own Excel program because depending on the version you're using, it may not be compatible with my archaic version that I dug up from underneath a museum or something. I don't know. All right, so in quantum mechanics in chapter 3, we have talked about line spectra and also how light can be used as a tool to observe the electronic structure of atoms. What we're going to do is we're going to examine the hydrogen spectrum because hydrogen is very simple. It's just one electron and one proton. That system we can model pretty effectively with the equations that we've studied. So, like the Bohr equation, where you have that 1 over n squared term and then the Rydberg constant, and that equals 1 over lambda. We're going to calculate lambda based off of energy today. So we also know the equation E equals hc over lambda. I'm going to give you a different equation that just directly gives you the energy values of these orbitals. And that's explained in the experiment here. So we know these equations right here. I can't highlight parts of them, but I could just circle with the cursor. And we're going to equate the energy of the photon that a transition gives to whatever the difference is between the two states. So higher minus lower would then be the energy of the photon emitted if a photon fell from the higher energy level to the lower energy level. And remember that these energy levels are the principal quantum number n. What we're going to do is we're going to try and find the energy of a mole of photons so that we can get the energy in kilojoules per mole. The reason that we do kilojoules per mole is because that is a common unit used for energy. For example, when you get to organic chemistry or thermodynamics, thermodynamics is probably more relevant because that's 162. All of your energy calculations are going to be in joules or joules per mole. In other words, if I burn a mole of this compound, how much energy do I get out? Likewise, with atoms, we need to have the per mole part so that we can correlate this energy with other familiar units of energy. So the per mole part is going to come from photons. So what we're going to do is we're going to calculate the energy difference for a transition, and then we're going to times it by a mole of photons in order to get the energy per mole, which would be this right here. Sorry, that's what we're going to multiply by. So if I know the energy of one photon, I multiply by Avogadro's number of photons per mole to get the energy per mole. And that'll look like this. So really all I've done is taken the equation that we know and multiplied it by Avogadro's number. And then the next thing we're going to do is dimensional analysis so that we can get units into the units of wavelength that we're familiar with. So here what's going on in this equation is I have all these constants, which I've shown here, and the units of those constants need to be in 1 kilojoules per mole, so we need that. And also we want to work with wavelength. So that's just what this equation is doing. It's converting the speed of light into nanometers per second instead. And then adding this term so that we get kilojoules per mole. then basically what we're doing is solving for wavelength. So this is all algebra that you can work through and look at to say, okay, we started with an equation that we understand of here. This is the energy per photon. This is the energy for 1 mole of photons. This is the energy in kilojoules per mole for a mole of photons. And if you add in all the constants and you put in all the numbers, here's the units and the numbers that you get. Then we just rearrange for wavelength. My wavelength is in nanometers because when we are putting stuff into Google, nanometers is going to be a useful unit for us to identify, oh, that's a visible wavelength, because we know what the visible wavelength is for light. It's 400 to 700 nanometers. We talked a little bit about that in the Beers Law lab, and we've talked about that in the lecture when I showed you the visible spectra. Since we're looking at hydrogen, we want to know what the transitions are for hydrogen, and if you remember, there are 4 principal lines that we saw. There was the red one, the cyan one, and then the 2 purple ones. And I think I show that. Let me see if I have a picture of that. I don't think that I do, now that I'm looking at it. That's okay. All right. So this equation right here, equation 5, is in bold. This is the equation that you're going to be plotting into Excel. I shouldn't say plotting. You're going to be entering it into Excel. And it's going to spit out wavelength. Now, that's not difficult to type in as long as you know what this number is, delta E. We're going to try to calculate that in a second, but first I'm going to show you how to enter an equation into Excel. So we're going to open this up here that I have prepared. And so I'm going to just pick any cell here. And so what I'm going to do is I'm going to tell it, I want this to be an equation, so I'm going to hit equal. Starting any cell with equal programs Google Sheets to say, hey, this is a formula. What I'm going to put in there, I should calculate. And so that could be something like 5 plus 3. And when you hit enter, it should return 8. Now, you could also do stuff like this, where I could say, okay, instead I want you to add this cell, that says H35, plus whatever's in this cell, which would be I35. Now, there's nothing in there, so it's going to put 0. But if I enter numbers in here, it will then add them, and I can do whatever I want to, and it will update it on the fly. How do you do Sig Figs in Excel? Okay, so let's suppose that you wanted to enter 13.000. This is what it's going to do, right? Boop. That's not super useful. So what you need to do is if you want more... Oh, can't see? Oops, that's not what I wanted to do. Hold on. All right. The problem is you're not going to be able to see what's at the top now, unfortunately. And I kind of need that. So you know what I'll do? We'll just cover the chat for a bit. So you got... I can still see you guys, but... Oops. I do want the top of this to be visible because we're going to use it. Whatever, right? We'll just cover everything. Okay. So, if I want more sig figs for this number, there's a button right here that says decrease decimal places or increase decimal places. I can toggle that, and you can see it's affecting my answer, but I can do them independently if I wanted to. So if I did something like this, and I only wanted my answer to be reported to 4 sig figs, it would round off that 0.25 there. But if I do this, it would then retain it. So it knows what all the numbers are. Now, in this experiment, I'm just going to say let it spit out whatever numbers it does. And that's where the instructions for disregard the sig figs are. This is just because you asked me the question. So, when you type in these equations into these boxes, you're going to get large numbers, and formatting them all for sig figs is super tedious, and it's kind of not the point of this experiment anyway. The point is for you to play around in Excel and learn how to plot functions, and then also see what you're trying to do with the numbers. So let's go back to what the equation was that I wanted to do. So if I hide this again, I wanted to plot 1.196 times 10 to the minus 5, or 10 to the 5, divided by energy. And if I do that, I should get an answer in nanometers. Now, You can't put units in Excel, so we're going to ignore them because the answer will come out in nanometers because all of this stuff cancels except nanometers. And we'll just indicate that in a table. So let's just show how to do that. So if I wanted to do that function, I would say equals 1.196 times, which is the asterisk, 10 to the caret 5. That's a little low on the screen. Hold on, let me do this. I'm putting it outside of the table because that's my just workspace. You're going to put it in the table, but there's another part to this equation that we have to deal with. Now, you'll notice that I had to add in divided by delta E. We haven't actually gotten to that part, but if I click here, it's not going to let me do anything. So if you need to edit the equation, go up to the bar up here and type it in. So now I would do divided by, and now I got to find out what delta E is. So delta E is going to be some cell somewhere, right? So I could just click, okay, I want it to be parentheses, this one, whatever that is. Now I'm going to get divided by 0 because there's no number here. But if it was 3, it will tell me what that is. So that's just the gist of how to type in formulas. Make sure you're using parentheses. If you have incomplete parentheses and make a mistake, it won't know what to do. And it will try and put in a parenthesis for you sometimes, but not all the time. Okay, so we're going to delete that. Let's figure out how to get that delta E part, because that's where this table is going to come in right here. Write the formulas used to calculate the energy levels for n equals 1 to n equals 10. So here's how we do that. So in order to figure out the difference in energy between the two energy levels, we need to know what those energy levels are, right? We need to know what E of higher is and E of lower is. So let's talk about how to do that. I'm going to show you a diagram here for sodium with some energy values that have already been calculated. So you might remember when I was drawing the diagram with the nucleus at the bottom and then n equals 1, n equals 2, n equals 3, etc. that I assigned 0 to n equals infinity, and that was for ionization. And what that means is that if I have an electron sitting here at negative 495, and I want to ionize this atom to remove the electron, so move the electron to here, so the electron doesn't see the nucleus, I would need this number and this number, the difference between them. So I'd have to add 495 kilojoules to get it up to here. In other words, final minus initial would be 0 minus this negative number, or positive 495. If I wanted to find the difference between these two to get from negative 292 to 187, I would just say, okay, final minus initial, negative 187 minus negative 292. And that'd be like positive 105 or something. So the gist is you're going to calculate these numbers using a formula that we give you. And that's going to represent the energy values for each n. So n equals 1 will have an energy. N equals 2 will have an energy. N equals 3 will have an energy. And these numbers should be negative, but they should get smaller and smaller and smaller as you get closer and closer to n equals infinity. So I'm going to show you how to do that using the formula. This right here is just showing the calculation of how to get a wavelength. We're going to do that in a second, so don't worry about that. All right. Here's the Rydberg equation. This is the formula for wavelength related to energy transitions, right? We're going to change this formula into energy by using E equals hc over lambda. I could substitute out lambda, and then that would give me this equation, which we then times by Avogadro's number to get it in kilojoules per mole. Now, to figure out the energy of a level, what I need to do is I need to set one of these as a reference. And the reference that we picked again up here is that at n equals infinity, energy is 0. So we're going to set that right here. I'm going to set one of these numbers to be n equals infinity. That's this one. And so that term just drops out because 1 over infinity is 0. And then our equation becomes this. Notice that my minus sign moved out of the front here. So this minus sign that was right here is now over here in the equation. So what we're going to do is we're going to plot this equation once we've got all the numbers in there, and that will tell us the energy in kilojoules per mole of the energy level. And so when you do that with all the numbers, you get this. And I have already done that for you. So every energy level will have this as its energy value. So n equals 1 will be minus 1,312 kilojoules divided by 1 squared. So what we need to do is put that into our spreadsheet. So let's do that. So we need to make a table. And whenever you make tables, let me make sure I have enough space here to do that. Yeah, I do. Okay. You should label what your table is. So I'm going to call this first column energy level. And the second column is going to be energy in kilojoules per mole. Now, if you want to be more specific, you can always just like write more stuff in here. But you'll notice that it kind of gets lost because there's not enough space. So feel free to move these bars around if you need to. You could also just type N. Like, we know that this is N. So now I'm going to type in all those numbers. 1, 2, 3. That's really tedious to do it this way. So a better way to, instead of typing in all the numbers, would be, okay, I'm going to select a pattern here. Let's pretend that I only did these two. I'm going to select those two and then click on this and just drag it down. And Google Sheets will automatically repeat what it thinks you're trying to do, which is, oh, it's incrementing by 1. Okay, I'll do that. Now notice that when I did that, my table formatting broke, so there's no border here. I don't give a shit about the borders. I'm just trying to make them look nice for you guys. You can destroy all the formatting you want, as long as you put everything in the spots that I expect it to. So don't make more work for yourself, especially when you're typing in formulas. So we learned that the formula was negative 1,312 kilojoules per mole divided by n squared. Now I could just do this, 1 squared, and then type the same thing again, 2 squared. But that's going to be super tedious again. So what we're going to do is we're going to type in the formula like this. Negative 1312 divided by this number, and I'm going to click on it, squared. Now, if you're concerned about order of operations, put parentheses in there. What it's going to do is take 1,312 and divide it by 1 squared, and it should give me the same number as it did before. Now what I can do is tell it to do the same thing in all of these cells. So if I were to copy this formula here and paste it here, it'll do the same thing again, but it does it relative to where your formula is. So up here, I told it to, okay, in the cell I'm computing, take the number to your left and square it. It's going to do the same thing here. Okay, now take the number to your left and square it, and then 1312 divided by that. And if I keep pasting this formula, it will just keep doing that. Now, if you don't want to sit there and copy paste, I can't blame you for that. Do the same thing we did over there, and it will just repeat the pattern. Then you can adjust this for, oh, I need more digits. Or you could just chop down Sig Figs if you want to. I'm going to just suggest to leave it how it is. So these are the energy values for our diagram. So if we were to, actually, you know what, let me just get Photoshop open here. Because I feel like this is worth illustrating. I didn't actually load this, so there we go, it popped up. I gotta get my tablet out too. So if I was to draw this diagram that we've been doing all quarter, well, all Chapter 3, which is all quarter, basically. We know that n equals infinity is 0 kilojoules, because we've defined that, right? And now I can just look at the numbers that this spit out. So let's see here. So 1 was negative 13, 12, kilojoules per mole. Now, 2 was negative 328, so we're just going to write these in, negative 328. And then number 3 was minus 145.7. And then dot, all the way up to n equals 10. And then 10 was just negative 13.12. So what that means is that now I know the energy difference between all these levels. So if I had an electron and my electron went from, say, n equals 3, here's my electron, and it falls down to n equals 1, I could say that energy difference would be E3 minus E1, right? And so that would be the amount of energy lost by the atom in doing that. But we're observing the photon that comes out instead. So what we're going to do is we're going to take the negative of that to get our result, which would be the same as me just writing this, or final minus initial. So if I do negative 13.12 minus, wait a second, hold on. My sign is weird here. I do want E3 minus E1, but why did that not work out? Hold on just a second. I'm confusing myself here with my notation. So if I do this, I'm going to get a positive number, which is what I want. I want my number to be positive. And so negative 145.7 kilojoules per mole minus negative 1312 kilojoules per mole. So let's see here. So this difference, I get this number. So that's for the difference between energy level 3 and 1. Now, if we go back to our PDF here, right here, that number that we just calculated, delta E, goes here in equation 5. Right here. So once I know what delta E is, I then know what lambda would be for the wave that's coming out of that. So that's what we're going to do, is we're going to plug that into the spreadsheet. So let's do that. So what I'm going to tell it to do is I'm going to say, okay, I want to first start by doing transitions from n equals x to some number. And I'm going to start by going n equals 1. Excuse me. So what this means is that I am going to start at n equals whatever this number is that I choose and go to 1. So the first transition will be 2 to 1, then 3 to 1, then 4 to 1, then 5 to 1, then 6 to 1, and so on. Then I'm going to type in the formula. And the formula we're going to use over and over and over and over again is equation 5. So if we look at equation 5, I want to type in 1.196 times 10 to the 5 divided by delta E. Oops, that's the wrong window. 1.196 times 10 to the 5 divided by delta E. And we just said delta E is going to be for 2 to 1 right here, right? So I'm going to go divided by my energy for number 2 minus my energy for number 1. And then I'll hit enter. That's my energy turned into a wavelength. Now, if I wanted to go from 3 to 1, I would just tell the formula up here to reference the number for 3, and 4, and 5, and 6, and so on. So you'd think, I could just do this, and it would be done, right? But there's an issue here. And the issue is that when I look at what my formula is referencing here, so if I click on this, and I double click and I do this, it's referencing these two. That's what I told it to do. But then when I click on this next one, oh, it moved both of them down, but I only want one of them to move down. I want this first number that I'm referencing to just go down the list. But the second one needs to stay put. And so what do you do to fix that? Well, first let's undo what we did here. To get a cell to not move and just to constantly reference what you typed in, what you go up and do is in front of the letter you type a $, and in front of the number you type a $, too. And what this tells Google Sheets or Excel is that, okay, this reference is locked. I will always refer to C12. Even if you move the formula, I won't change what that position references. Notice that this other one doesn't have $signs in front of it, so this one will just be referenced based on position. In other words, oh, you want me to refer to the cell that is 1, 2, 3, 4 over and 1 down. I can do that. So this, when I repeat the formula here, it will refer to this number, and this one will refer to that number. And that's exactly what we want it to do. So now when I drag this out, you'll notice that my numbers are actually getting smaller. And that makes sense because a smaller wavelength corresponds to a higher energy, right? And if we go back to here, oops, that didn't work. There we go. Remember that as I fall from higher and higher levels, E is increasing, which means that lambda is decreasing. So when you do these calculations, what you should find out is that the difference between energy levels should get bigger as you go from n equals 1 to n equals 2 to n equals 3, or whatever number you're picking, down to wherever your goal is. And as you do that, the wavelength should decrease. All right, I need just a second because I want to make sure that I format this similarly to what you do in the lab. Now, in the lab documentation, I actually walk you through how to do this like in excruciating detail. So like we could do all of this like one step at a time. But if you follow this, you're going to get the gist of what we're doing here. I'm just making sure that I've matched up the columns here. Give me just a second here. Sorry, that's going to get really small. Okay, so what my directions apparently are asking is that you want two numbers in here. And I inadvertently gave you the second number. Okay, so let's Let's clear everything here. And I'll show you what it's supposed to look like. So let's see here. So the first column will be delta E. I'm just going to write dE for n equals x to n equals 1. We'll just make that a little wider. That's fine. And so this column is just going to calculate changes in energy. So I want this one, this first one should be n equals 2 to n equals 1. So that'll just be these two numbers subtracted. Oops, didn't mean to drag that over there. So this will equal this number minus this number. And then we'll just repeat the command, except I need to go up here and do this. So that when I do this now... Oh, god damn it. I'm sorry. Okay, let me do that again to show you what I was doing. Sorry about that. I have 5 windows open at once, and I'm like looking every which way. So, okay. For this giant table you're going to do here, you're going to have alternating columns. The first column is going to be delta E, and then the next column is going to be wavelength. I'm just going to write wavelength. So let's figure out the energy difference between... So X means whatever number I'm looking at, dropping down to n equals 1. So this box right here will be the energy for for level 2 minus the energy of level 1. I'm then going to go and edit the formula and put dollar signs in there so that I'm always referring to level 1 in this calculation. Then the next one down should be 3 to 1, and then 4 to 1, 5 to 1, 6 to 1, 7 to 1, 8 to 1. So 2, 3, 4, 5, 6, 7, 8, 9, 10. There are all my delta E's, right? So this should be 10 to 1, which is just this number minus that number, and that checks out. And then what we're going to do for the wavelength is we're going to turn this number written here, we're going to turn that energy into a wavelength, and that's where you use equation 5. So I had skipped a step. So let me find equation 5. So that looks like this. There it is again. 1.196 times 10 to the 5 divided by delta E. Delta E is now just the number directly to the left of your calculation. So you're all set there. So 1.196 times 10 to the 5 divided by delta E, which is just that. And apparently Excel tries to Google Sheets suggests an autofill, which actually in this case is fine. So it has entered all those numbers in for us. So these are the wavelengths for all the transitions from n equals x to n equals 1. So this would be 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1, 7 to 1, 8 to 1, 9 to 1, 10 to 1. Cool. Now let's do that for n equals x to n equals 2. And we'll make this... Oops, that's not what I meant to do. We'll make this a little wider. So now I want n equals 2 to be my endpoint. Well, if I started at 1 and then ended at 2, that's not energy being released. So I'm going to omit that one. My first entry is instead going to be 3 to 2. So that's going to be equals energy of 3 minus energy of 2. And then I'm going to lock in the reference to energy cell 2, because I want to now do 4 to 2, 5 to 2, 6 to 2, and so on. So here it would go 4 to 2, 5, 6, 7, 8, 9, 10 to 2. If I went down all the way to the bottom, I should have an error. And that error will be, I'm trying to refer to a cell that's blank, right? I went off the table. So this last row down here isn't even going to have a formula because we don't have n equals 11. So this will be 3 to 2, 4 to 2, 5 to 2, 6 to 2, 7 to 2, 8 to 2, 9 to 2, 10 to 2. And as you do these, they're each going to go up. And this table keeps going for quite a ways. Every time you do your formulas, the next one's going to have one fewer. And eventually you'll get to the last transition all the way at the far end of the table. Oh, it's not letting me do... Oh, I was clicking the wrong thing. Which you can't see. It's over here somewhere. Which will be 10 to 9. So let's turn these energy values into wavelengths. And so that's going to be equation 5 again. 1.196 times, oops, not x, 10 to the 5 divided by the number right here. And sure, we'll autofill it. It tried to do this because there's no number next to it, so we'll erase it. There you go, there's all our wavelengths. We'll just put in a title, wavelength. Now, if we wanted to check whether this is doing this correctly or not, you could refer to known numbers. And we know that if we calculate the energy difference between wavelengths from n equals 3 to n equals 2, we should get it red, right? Because we did that example in class. We learned that all the emissions for hydrogen are from n equals a higher number falling down to n equals 2. And so that means that this first one right here should be 3 to 2. This should be 4 to 2, 5 to 2, and 6 to 2. And if you remember what color red is about 650. So we have set up the equations correctly. I've shown you in this video how to do n equals whatever to 1 and also whatever to 2. What I want you to do now is I want you to do... Oops, not n equals x. There we go. I want you to do it for n equals 3 and a wavelength. And then to n equals 4. And then 5, and then 6, and then 7, and then 8, and then 9. And 9 will be the last one because the last transition is 10 to 9. So you're going to, and you can't see this, but I got to make it smaller to show it. This goes all the way over. So you're going to have 100 or so transitions here, which is, it sounds ridiculous, but I just did 19 of them in no time at all. Like, we've been lecturing for, what, 30 minutes on this, and I've only spent about 10 minutes of this actually talking about this equation part. So these go really quickly once you get it plotted out, and once you have everything set up, you're done. Like, that's the experiment. This is all you're doing. Now, because this is an online class, obviously you can talk to each other in Discord and share information. I would really, really strongly encourage you to do the work yourself and not just somebody figure it out and then pass the Excel file around. Because one, the whole point is for you to learn how to do Excel, and Google Sheets is based off of Excel. That's why I keep saying Excel. So the whole point is for you to play around with these commands and figure it out. And in later classes when you're going to need to use spreadsheets to do these sorts of commands, knowing how to do this can save you a lot of time. So invest the few hours in just typing in these commands. And if you get stuck or something, take a picture and paste it into Discord. So for example, maybe I have like a formula error or something. Like I do, I don't know, like I do that. And I get a bogus number. Here, let me clear most of these out here. I get a bogus number, and I'm like, I don't know what's going on. Okay, well, hint print screen on your keyboard, or alt print screen, and paste it in Discord. Make sure you have selected what your cell that has the error is, so I can see this. This is the part that I need to see, is the formula. If I can look at the formula, I can debug your answer, and I can tell you, oh, you put a $sign where you needed to, or you forgot this caret here, or something like that. So if you have any issues with this at all, I can totally debug them. Just take a print screen. It's very easy for me to figure this out because I've done Excel for years, and it's super powerful if you know how to use it. I have to now hit Control Z a lot because it will fix my formatting. There you go. Because I foolishly am drawing on the document that I'm giving to you guys. All right. That's part A of the experiment that uses Excel. Down here is a box that is going to ask you to figure out which transitions are from the Balmer series. Now, the Balmer series is the visible spectrum. So what you're going to do is once you have all of your transitions plotted out, you're going to go and highlight the ones that are Balmer series, and then just paint them another color. So go up here and then paint them purple or something. I don't care. You pick any color you want to. You just need to distinguish them so I can see them. And then down here, you need to compare what you saw in the video to your results on this screen. And then there will be other questions for you to answer in the pre-lab analysis. All right. That's part A. And it's just a bunch of Excel directions. So I think part A is far more confusing than part B myself. Part B makes a lot of sense once you've seen me do one of them. And we're going to do one of these together. So part B is called Photoemission Spectroscopy. And what photoemission... Oh, it's photoelectron spectroscopy, because we're not emitting things. We're actually ejecting electrons with photons. Photoelectron spectroscopy is basically this. I'm going to draw a picture of it. Okay. I'm going to actually hide this layer, because we're going to come back to that in just a second. So let me make a new layer, and we'll draw on that one. All right. So what this is here's my atom, and my atom has an electron around it, and there's the nucleus in the center. If I shoot it with a photon, and it has enough energy to get from n equals wherever it is to n equals infinity, then the electron is free, right? They're separated. If I give it a little bit more oomph, then my electron will have a velocity associated with it, right? So the energy to eject the electron should be whatever the ionization energy is. And we'll talk about ionization energy tomorrow. Plus whatever the energy was to give it kinetic energy. In other words, if my electron is moving and hits the detector will go, oh, this had kinetic energy equals that, and the photon had energy equals that. I'm going to subtract the two to get the energy of the energy level. So if this was an n equals 1, I shoot a photon at this electron. It now is n equals infinity. It has a little bit extra energy, which I can detect its velocity with. Now, what does that mean for our purposes? What this means is that the spectrum that is going to be printed out is going to look something like this. So on the y-axis is energy. Sorry, that's not right. On the x-axis is energy. And I think that we actually have megajoules per mole here. And on the y-axis is just intensity. And so what this does is it will say, okay, I'm going to examine, let's just say hydrogen. And so it's going to go like this. There's my one peak for hydrogen. And what this is going to say is that there is a electron that has this energy associated with it. We've already calculated that. It should be... Oh, sorry, this is in megajoules, so let me just put a dot there. That should be n equals 1, because that's where the electron is, right? So you're going to get a bunch of diagrams that have these humps on them and energy levels, and that's going to represent where the electrons are in the atoms. So PES scans atoms and tries to find where the electrons are at the ground state, what their energy is. Now let's suppose that I picked something more complicated, say lithium, then what the spectrum would spit out would be something like this. And so there would be 2 humps for lithium. Now, why would there be 2 humps for lithium? Well, there are 2 different places, according to this PES, that electrons live. What are those 2 places? Well, we know how to draw electron diagrams, don't we? If this is lithium, what are the 2 places you would find electrons? You'd find them here and here. So one of these humps must be 1s, and the other hump must be 2s. But which is which? Well, there's 2 ways to tell. The first is to use the x-axis in energy. Going in this direction is increasing energy. Which orbital has the higher potential energy, according to the diagram? Which one's harder to remove, 1s or 2s? What do you think? Type it in the chat. What's harder to remove, a 1s electron or a 2s electron? So that we can get it from where it lived to the detector. And remember that removing it means getting it up to n equals infinity. Yeah, 1s. 1s is way harder, right? Because it's closer to the nucleus. It's further away from n equals infinity. So, the peak with more energy should be 1s, and the peak with less energy should be 2s. Now, the other way to determine which peak is which is to look at how big they are. Intensity is just how many electrons it detected, right? Well, if I'm ripping out all the 1s electrons and I'm ripping out all the 2s electrons, and there's twice as many 1s electrons as there are 2s electrons, the peak should be twice as big, right? So when you're looking at the PES spectra, you have to consider both these things. You have to look at the energy, which is the x-axis, and then you have to look at the intensity, which is the y-axis. Now, intensity has been plotted on the PES diagrams as area. What that means is that if you know calculus, you know that you can integrate the area under a curve. So I could figure out how much space this is, and that would correlate to some number of electrons. And then I could figure out how much space this is, and that would correlate to some number of electrons. And since this area is twice as big, it must have twice as many electrons. So integration is a very common spectroscopy technique to figure out relative areas. So let's look at the PES worksheet, and we're going to do some of the examples. I'm not going to do all of them because that's kind of the whole point. So we're going to start with neon. This is the screen that we see for neon. So here's what I'm going to do. I'm going to go print screen, and then I'm going to go over to this. We'll get rid of this layer. And then when I hit... Oh, I didn't copy the thing for some reason. Hold on. Oh, there we go. It showed up this time. And now I gotta actually click on this. Okay. So let me crop out all this crap that we don't care about. That's not the crop tool. There we go. All right. I didn't copy the area of the peaks, but... Okay, so let me write down the area of these peaks, and we'll draw directly on the diagram here. So we've got This area is 90. This area is 29. And this area is also 29. And you can see that the energy on the x-axis is, this energy is 2. This is like 4.5. Sorry, let me try and draw that a little better. And then this energy is 84. And what the questions are going to ask you are things like, how many electrons are there? What's the structure? What does each peak represent? Well, let's look at what we already know. First of all, this is neon. So if I was going to draw the energy diagram for neon, it looks something like this, right? 1s, 2s, 2p. And there's 10 electrons, so go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That would be neon, right? So let's try and correlate this with the diagram. First of all, which orbital will have the highest energy? Is it 1s, 2s, or 2p? In other words, if this is n equals infinity, which electron is the hardest to remove? And you've already answered that, right? It's still 1s. So the 1s orbital should have the highest energy. So this orbital, which has the highest energy, is 1s. Now, we talked about how n equals 2, when you have lots of electrons, you start to split the energy levels, right? S is lower in energy than P, which is lower in energy than D, and so on. The PES actually lets you see the difference between those energy levels. Of these two peaks, there's a peak at 2 and a peak at 4.5. Which one is 2s? Energy 2 or energy 4.5? Which one is 2s? Type it in the chat while I drink some more water. You could also say left peak or right peak. This is pretty small on the screen, I just realized. Yeah, very good. So 2s should be this one because it's the next highest in energy, right? So getting my electrons all the way up to infinity takes energy. And the easiest ones to remove should be 2p. So this must be 2p. Now let's look at these area numbers. I have area 90 and 29 and 29. What the area numbers are like are relative amounts of electrons. Now, obviously, there's not 29 electrons in the 1s orbital in neon. That doesn't make any sense. But if I had ionized 29 atoms, sure, I could detect 29 electrons at that energy because each one had so many or whatever, right? So what you need to do is these peaks or this area tell you the relative number of electrons. So if I take the ratio and I divide by the smallest common number, I will get that. Because 29 is really close to 30, right? And so if I do a little bit of rounding, I can get everything to be 3 to 1 to 1. So what this says is that the first peak has 3 times as many electrons as the second peak and the third peak. Well, let's see if that's consistent. Here's the first peak. Does it have 3 times as many electrons as these two? And the answer to that should be, well, duh, yeah, it does, because it has 3 orbitals and these only have 1. Now be careful, because this is telling you the relative number of electrons. Relative electrons are not the same as actual electrons. If this was actually electrons, this would say that 2p has 3 electrons in it, and 2s and 1s only have 1 electron in it. Which is not true, because we know that orbitals have 2 electrons before you move on to the next orbital, right? So some of the questions are going to give you interesting results that you have to think about for a little bit to realize, oh, half of my electrons aren't unaccounted for. I just need to multiply everything by 2 because there are 2 electrons in an orbital. So be careful about that. You won't have to do that for every question, because sometimes you'll have a peak that has 1 electron in it, and other peaks will have 2, and then your ratio will work out when you divide by stuff. You'll get numbers that make sense. All right, so I'm going to skip helium because helium is very simple. We're going to go do an unknown. So we don't know what this is, and I'm going to try and get the energy values on the screen so I can print screen everything. There we go. Print screen. Paste. That didn't quite work. Hold on. Oh, it's because I cropped it. Okay, so let's just do that. There we go. Okay, give me a second here. Oops, I don't want the round ellipse tool. I want this one. All right, so I'm going to do this, and then that, and then that, and then we'll just zoom it in. There we go. All right. Our goal is to figure out what this is. So there are 4 peaks. And, oops, that's not what I meant to do. We've got 0.74 for our energy, 5.31, 9.07, and then 126. All right, I want you to tell me what you think each of these orbitals is. So, like, which one's 1s? Which one's whatever? Type it in the chat. And then I'm going to ask you, why do you think that? So, be prepared to write, like, a short answer. And if you're right, I will add it to the diagram. If you're wrong, we'll talk about it. We'll try and go over what's going on there. Now, if you're stuck and you're like, I don't know which orbital is which, try drawing the electron configuration diagram for an element that's just empty. So just start ordering your orbitals in order from lowest to highest energy using the Aufbau principle. You don't have to put any electrons in there just yet, but that will help you assign orbitals to each of these peaks. And there's also something important to note in that down at the bottom it says the 2 portions of the spectrum are drawn to different scales, so the height isn't something you can really refer to. You want to refer to the area. And only the portions of the spectrum containing peaks are shown. So these are all the peaks. There's nothing between 18 and 120. Nothing is omitted. So label these orbitals with their correct designation. 1s, 2s, 2, whatever. I'll give you 2 or 3 minutes to try it. Type it in the chat when you're done. All right, so we have an assignment of peaks, and that is the correct assignment. So let me get a new color out here, and we'll label them with your assignments of peaks here. So you said 1s, 2s, 2p, and 3s. And that's correct. Very good. And I'm assuming that you meant when you wrote 0.74, you wrote 1s2. I'm assuming you meant 3s2, because you had already said 1s2. And everything else was correct, so. There you go, perfect. That's exactly right. So all the s orbitals are kind of short, right? They all have the same area, because they all have the same number of electrons. And the p orbital is like 3 times as big. So that's exactly what I want you to do, is something like that. And this is magnesium, very good. There you go, you solved the unknown. Now, the questions that are on this document will kind of guide you through that, and they're going to ask you, like, label the peaks. Then the next thing they're going to ask you to do is calculate relative numbers of electrons. And so you just did that. So you said, okay, well, this is 3 times as much as these guys. And so that must mean that this is probably true. And I know that an orbital in the nest that's full, because the lowest level stuff has to be full, has to have 2 electrons in it, right? And there you go. That's exactly the logic process that I want. That's perfect. Now do that with the other unknowns. So I don't want to do all the unknowns because I think there's only 3 of them, right? Let me check how many unknowns I have. If I had 4 of them, I would do a second one. Yeah, that's it. That's all the unknowns that I have. Number 2 is just like this. Unknown number 2. Unknown number 3 has a trick to it. And the trick is that part of the information is a little misleading. And so we have to talk a little bit about what this is specifically for unknown number 3. On the diagram right here, you'll notice that I wrote this for data C. And that, oops, I didn't mean to go over that twice there. Like, this is always written here. Like, why the heck am I constantly writing this information? What that means is that this is the limit of the detector. And so that the x-axis stops at 140. Now, as you can see, we got to magnesium, and this 1s orbital is already pretty damn close to that limit, right? So what do you think happens if I happen to have a peak whose orbital is higher in energy than 140 megajoules per mole? Let's say like I ionized some element and it ended up having an ionization energy of 200 megajoules per mole. What would happen on the detector? What would you see on the graph? Why is this not sodium? The reason for that is because this peak has an area that is approximately the same as all the other peaks. You can see that down here. Oops, that was a really bad circle. So because all these peaks are the same, they must have the same number of electrons. If this was sodium, here's what the difference would be. That would be sodium. And then this peak would just be a little lower. But you're right, sodium totally has 4 groups of electrons, but the number of relative electrons in each peak would be different in the 3s peak. So this one would be smaller for sodium. Right, because in the 3s orbital for sodium, there's only 1 electron, whereas in all the other s orbitals, there'd be 2. So the detector is not only detecting where the energy levels occur, but it's also detecting how many electrons are in there. Now, back to my question here. What would happen if you had an orbital that had an energy higher than 140 megajoules? Where would it show up on the graph? Given this information that I keep writing. Yeah, go off the graph, right? You wouldn't see it. So in other words, what that means is that the detector cannot observe electrons that are above this number. So this is your limit. So energy above this won't end up on the graph because it doesn't go past that limit. So for one of your unknowns, you actually have this case pop up. And what that means is you can't just go down here and go, oh, I'm going to count all the electrons, because some of them fall off the graph. So what you have to do is you have to apply logic and then assume, okay, the highest energy one might not be 1s. It might be something else because other peaks are so high in energy they fell off the graph. Okay? But you can use the area to figure out the pattern of what it is because you know the ordering of orbitals. It goes like this, right? 1s, 2s, 2p, 3s, 3p, 4s, 3d, and so on and so forth, right? So if you get a chunk of a graph and you can see, oh, I clearly have these guys in here, and everything else fell off the graph, that would be easy because your relative electrons would be like 3 to 1 to 3 to 1 to 5 to 3. And so you could see that in the graph using the area. So the PES charts are like little puzzles. Obviously, you have to know what all of the pieces mean, but now that you know the ordering of orbitals and you know how to count the number of electrons in there using the area, and you know the ordering of the peaks based on the x-axis and the ordering of energy, you can then deduce what the substance is. And it will always be an element that's real. So these are all real elements. We're not just making up shit. If you aren't sure, you can always ask in the Discord what other people got and then try and explain it to each other. I'm going to try and like hit the brakes on me just telling you the answer. But if you're on the wrong track, I will try and point you in the right direction. So I can't tell you, oh, it's whatever it is. I almost said the answer. But I will say, tell me why you think that, and then if you have any errors in your logic, I'll correct them or point them out. And if it's correct, I'll say, well, I couldn't find anything wrong with it. It sounds good. Okay, so that's part B of the lab. That's experiment B. And then all the rest of the questions associated with these graphs are just like, do this thing with this graph, and then do this thing, and then do that, and then tell me why you did that. So when you go down to the Excel sheet, there's going to be just a bunch of questions that you just fill in all the answers to. And so that looks like this. So this is part B. You're just going to fill in all of these answers based on the questions. And I try to label like, okay, this is for chart B, this is for chart C, and so on and so forth. Okay. This was apparently the first lab where I realized, oh, I need to be telling you how many points each question is worth, just for my sake. So you'll notice that these are now labeled. I still have to go back and label the old ones. But yeah, that's how you do this. I went 20 minutes over the break, so we're going to take a break. I don't have my timer out yet, but let me start the timer real quick. I'd like to collect questions for 10 minutes. If you guys have any questions for me to answer when we get back, we'll do Q&A. I mean, it's quantum mechanics, right? There should be lots of questions, but if you feel like you kind of have an okay grasp of it, and also there's only 4 of you here. Oh, there's 7 people now. Okay, cool. Like if you feel like you have a good grasp on it, that's totally fine. Ask me questions when they come up in Discord. So we'll turn this on. We'll get more Zelda music going. We'll be back in a second. anyone has any quantum mechanics questions, let me know. Yeah, we're going to talk about sigma bonds at the end of the quarter. But only, like, very briefly. Like, this is a sigma bond. The bond orbitals overlap end to end. Hooray. And then I'll make you draw one, and then you'll have no way to show me that you can do that. Because I can't make you take a picture and upload it for an exam. I could do it for a lab. If you're taking 131 with me, my students have to take pictures of stuff all the time. Because it's all organic, so you have to draw stuff on paper and then take a picture and put it in your lab. But you don't have to do that for this class. I didn't get any questions about quantum mechanics, just generic, like, talking to people, which is fine and all. But I'm going to close down the stream then, because there's only, like, 20 minutes left. And if I spend 10 more minutes waiting for questions, we won't have time to answer them. So hit me up on the Discord if anything comes up. Try and do the lab. It is due next week. Let me know, like, be proactive about this, because this is not an easy assignment, and I realize that, having been the one that wrote it, and, we give this quarter to in-class students all the time, or we give this, experiment to in-class students all the time, and it's still really hard, and you don't have that, like, 2-hour, 3-hour period for me to, like, walk around and poke at your Excel sheet and then point at the diagram and show you. But with Discord, you can sort of approximate that. So use that, or send me an email. Let me know, whatever it is that you need me to do. Yeah, we're not doing stereochemistry in the 100 series. Do we talk about it later? I don't think so. I don't think we talk about chirality until 261. But yeah, I teach organic, so I find all that stuff super interesting. But we can talk about that some other time. Okay, some stuff moved around there. You could see why. Like, I had to. If you look down here at the very bottom where it says Cadence of Hyrule, like, it just slightly moves, and that really bugs me. So I screwed something up with that, and it was doing that earlier. So that's why I was 5 minutes late to starting the lecture, was because I had to reline everything up again, and that takes time. I hope that lab tutorial was useful. This is probably the most difficult lab by far. So please come back and refer to this video as you need to. And then ask me questions, again, Discord or email. Happy to answer them. Otherwise, have a wonderful rest of your evening, and we'll see you tomorrow for part X of a continuing series of quantum mechanics that never seems to end.